Welcome to Chemistry Lover, and in this video I am going to talk about very important topic, that is symmetry elements present in allene, its point group, and the other derivative of allenes, what are their symmetries, and last of this video I will talk about the symmetry number and what is its importance. So let's start today's topic. So in the previous video I discussed about the symmetry elements, symmetry operations, and the point group. Now from a point group, from a particular point group, you can tell that which symmetry elements are present in a particular molecule. For example, the point group of BF3 is D3H, right? So from if someone tell you that a point group of a molecule is D3H, you can easily tell that which symmetry elements are present in that molecule. For example, in BF3 we can say that okay, it has C3, it also has perpendicular C2, and that will be 3 perpendicular C2 because it will always be equal to number of n, and then it will have sigma H and also it will have sigma D, right? So now this allene is very important, and questions most often question comes from either from direct allene or some derivatives of allene. So if you understand the proper stereochemistry and the symmetry elements present in allene, half of your stereochemistry syllabus is covered, right? So it is very important, and first we have to understand the bonding in allene and the planes, different planes present in allene, and what is the actual shape of the allene, right? So for that, you can see this is the molecular orbital picture or the orbital diagram, that is orbital picture of allene, where you can see the 4 hydrogens are not in the same plane, right? So if you take ethylene, for example, if you take ethylene, in this case all the 4 hydrogen atoms are in the same plane, right? And it is the molecular plane of the molecule. But this allene is very different from ethylene, and we can compare allene with some tetrahedral molecule like methane. So methane is tetrahedral. You can see this is the structure of methane. So in methane, what happens? 2 of your hydrogen is in a plane, these 2 hydrogen in a particular plane, and these 2 hydrogens are in other plane, and these 2 planes are perpendicular to each other. So if you just imagine that these 2 hydrogen you take and these 2 hydrogen take, and you just stretch these 2. So this is why allene is sometimes called elongated tetrahedron, right? So if you elongate a tetrahedron, that will give you the allene structure. Now that means the 2 pi bonds present in allene, this pi bond and this pi bond, they are not in the same plane. So one pi bond is formed by let's say we take that this is the z axis, this is your x axis, and this is your y axis. So in case of allene, one pi bond is formed between the 2 pz orbitals, whereas the other pi bond is formed between the 2 px orbitals, and in this case we take the molecular axis as x axis, right? So it is for sure that 2 pi bonds are not in same plane, and also the 4 hydrogens are also not in same plane. 2 in one plane and other 2 is in other plane, and that is shown beautifully in this picture. You can see we consider these 2 plane. One plane is just coincident with the board or parallel to the board, and another plane which is bisecting the board or perpendicular to the board, and that plane is xy. So xy plane is perpendicular to the board and yz plane is parallel to the board. Now these blue hydrogens are parallel to the board, that is it is on the yz plane, whereas these green hydrogens, they are on the xy plane. Okay, so now if I tell that allene has D2D symmetry, so from or D2D point groups, so from this point group you can say that which symmetry elements are present in allene. For example, this implies that allene has a C2 axis, right, and it has D symmetry. That means it will have 2 perpendicular C2, because I already told that if a molecule has perpendicular C2, then only its point group will be D and not C. So in this case the point group is D. That means it will have perpendicular C2, and as the C2 is here, n is 2, that means 2 perpendicular C2 it will have. Now other thing is that D2D is symmetry. That means sigma plane is also there, and that sigma plane is not sigma V, but that is sigma D, right? So these symmetry elements are present in allene. and let me tell you that another symmetry element is also present, that is basically S4 symmetry. So now our work is to find out that how these symmetry elements are present. So for that we have to look this molecule very carefully. If you just see this molecule, it is very difficult to find out all these symmetry elements, but there is a trick to find out how these symmetry elements are present in your allene molecule, and that I am now going to show you, right? So for that I have to represent this molecule within a cube. So let me first draw a cube like this. So this is a cube, okay. Now I can draw this allene inside the cube. So let's say this is your allene molecule, right? So I represent two of the hydrogen here, one is here and another is here. Basically you have to put this, so first you have to put these two hydrogens any of the two corner of this cube, and their two corners should be opposite to one another, that is this corner and this corner, not this and this, because they are adjacent. You have to put them opposite. Now so let's say this is hydrogen 1, this is your hydrogen 2, right? Now we have to put the another two hydrogen which will be opposite to these two. Okay, so this hydrogen we placed here, so next hydrogen we have to place here. So this will be our another hydrogen, and now another hydrogen we will place here, right? So okay, let me change the, so these are the four hydrogen atoms that we have to place within this cube. Okay, so let's say this is your H3 and this is your H4. So these are the four hydrogen atoms. Now let us imagine a axis which is along this particular axis, that is, let's say first take this as Z axis, this as X axis, and this as Y axis, and the Y axis is bisecting the board. Okay, so now let us consider a rotational axis which is along the X axis. So if we rotate it by 180 degree, what we will get? We will get this hydrogen 1 in the position of hydrogen 2 and hydrogen 2 in the position of hydrogen 1, whereas this hydrogen 3 will go to position of hydrogen 4 and hydrogen 4 will come to the position of hydrogen 3. That means by this 180 degree rotation we will achieve the same arrangement of the molecule. That means we can say that C2 axis is present in the molecule, and that C2 axis is basically the principal axis. So why it is principal axis, that will be clear in a moment. So next what we can do, we can imagine another axis from here which is just from the center of the molecule, but now in this case it is along the Z axis. So if we rotate this along this axis the molecule, then what we will get? We will get this hydrogen 2 in the position of hydrogen 4 and hydrogen 4 in the position of hydrogen 2, whereas this hydrogen 1 will go to hydrogen 3's position and hydrogen 3 will come to hydrogen 1's position. So that means in this case also we get the same arrangement of the molecule. So in this case another C2 is present here, and the same thing can happen when you consider an axis along this Y axis. For Z and Y the situation is just same. In this case this hydrogen 1 will go to hydrogen 4's position and 4 will come to 1's position, whereas 3 will go to 2's position and 2 will go to 3's position. So again another C2 is possible. Now if in your molecule you have more than one axis and among which is the highest pole axis, that is for which the n is highest, that is principal axis, which I discussed in the previous video. But in this case you can see all are C2 axis, that is n is same in all cases. Now how we would decide that which is the principal axis? So in this case the rule is that the axis which is penetrating the highest number of atoms, that will be considered as the principal axis. So in this case you can see the axis which is along the X axis, that is bisecting, that is penetrating 3 carbon atoms, whereas other two axes are penetrating only central carbon atom. So that means this axis which is along the X axis, that is considered as the principal axis. So this principal axis is actually this C2 axis. And now another interesting point is to notice that other two C2 axes, they are just perpendicular to this principal axis, and that's why they are perpendicular C2. And in this case you can see as the principal axis has n fold, so that means it has two C2 axis. So this is how we find the C2 axis of the molecules. Now to find out this sigma d is very simple. You can see I have already drawn the planes here. So this is one plane and this is another plane. These two are basically the sigma d planes. Okay, so these are basically one sigma d and this is the another sigma d. So these two sigma d's are there because it is not called sigma b, because you can see C2 axis is there. Now it is rather difficult to find out the S4 within this molecule. So but there is no problem, we can easily find out using this this cube representation. So for that we have to first rotate it, right? So if we rotate it by S4 means we have to rotate it by 90 degree. So 90-degree rotation will give you some arrangement. So let me rotate it here, right? So because we have to again take the mirror image. Now the 90-degree rotation of the molecule along this particular axis, this x-axis, will give you some arrangement like. So if you rotate it by 90 degree, what will happen? So let's say we rotate by this side. So that is basically clockwise. So this H4 will go here. So we will have the H4 here, and this H3 will come here, right? This is H3, this is your H4, and the other two, what will happen? This H2 will go here. So your H2 will basically go here, and this H1 will go here. Okay, so this is your H1. So this is new representation after the 90-degree rotation, that is rotation by 90 degree. Now we take a mirror image of the molecule. So let's say this is our mirror plane, and then what will happen? So again we have to draw a cube. So this is our cube, and just we have to now draw the mirror image of the molecule. So if you take the mirror image of the molecule, you can see one atom is here. So that means this will go here. So this is your basically H4, and another atom is here, right? So it will come here. So this is your H3, right? So this is your H4, H3, and these two, where it will go? So one will go like this here. This is your H1, and another will go. So another will go here. So this is your H2. So now if you see at this molecule and this molecule, you can see only the numbering of the hydrogen is different, but the two representations are exactly same, because you can see for this particular cube, one hydrogen is this corner, it has one hydrogen in this corner, next hydrogen is this corner, next is this, and another two are also same. So we achieve the same representation after 90-degree rotation and taking a mirror image along that particular axis. So that means this is basically a S4 operation, that is C4 into sigma, right? So that means S4 is present in this allene molecule. So this is for a normal allene molecule where no substitution is there. Now let us take the same allene, but in this case we will change our atoms, right? So in this case what we will do, so we will just take this type of representation where we will have this hydrogen, but now here we will have chlorine, and in this case here we will have hydrogen, and here we will have chlorine. So now what will be the changes in the molecule? So in this case you can see this rotational axis which was there along the x-axis, that will not be present, because if you rotate along this axis, this chlorine will go to the hydrogen position and hydrogen will come to the chlorine's position. So that means the C2 axis along this x-axis is destroyed. Okay, but another C2 axis which is along this y-axis, that is already present, because we can represent it like so. Here you have this chlorine and another chlorine is here. Okay, so now you can see that C2 axis which is along this y-axis, that is present in the molecule, because if you rotate it, this chlorine will go to this chlorine's position and this hydrogen will go to this hydrogen's position. So one C2 is retained, but other two C2s from the x-axis and z-axis, that C2 are vanished. Okay, and you can see no plane of symmetry is present, because if you consider a plane containing this chlorine and this hydrogen, that plane will not give you the mirror image relationship, because one group is chlorine and another is hydrogen. So it will have only the C2 symmetry. So for this molecule the point group is C2, right? Now let us change differently. For example, let's say here we put hydrogen, but here we put the chlorine, right? So now what can happen is that you can see in this particular case that C2 axis which is along that x-axis, that is present, that is this molecule will have a C2 axis, but the other C2 will not be there, because from the x-axis if you rotate it will not give the same arrangement, or from z-axis if you rotate it will not give the same arrangement. So only one C2 is there, but in this case the two sigma planes will be there, because if you consider a plane containing these two chlorine atoms, that will give you the mirror image relationship of these two hydrogens, whereas if you consider another plane which is containing these two hydrogens, that will give you mirror image relationship of these two chlorine atoms. So it will have 2 sigma V. So for this molecule the point group is C2V, right? Sorry, not D, this is V. So for this molecule the point group is C2V. So these three examples are very important from allene, and if question comes from there, it will come only from these three particular examples. Now another thing in this respect I would like to say is that you should be always careful while looking at the question, because in some cases they may give you this type of example. So if more than 4 carbons are there, so in this more than 3 carbons are there, that is, you can see in this case 1, 2, 3, 4. So 4 carbons are there, and in this case again it will be like ethylene molecule. So it will be planar and all the hydrogen atoms will be in the same plane. So in this case the symmetry will be same as for ethylene. So if you have odd number of carbon atoms, then it will behave like allene. Whereas if you have even number of carbon atoms, that will behave like ethylene. So this thing you have to notice while you are looking at the question paper. Why I am saying it? Because in the JAM exam, a question came from allene, and that is basically substituted allene, 2 chlorines were there, and I did the mistake. It was a very easy question, but I did mistake. And next in the MSc, this type of question came, and I again did mistake. So these are very little bit difference are there. So this difference you have to find out, otherwise you will do mistake, right? So this is one thing. Now this is the case of allene. So other molecules you can practice from D. Nashipuri book or any other book or any other question paper you can practice. These things just you need practice and you will be master of it. Okay, so after that what I will discuss is the symmetry number. So what is basically symmetry number? So symmetry number is basically the number of arrangement possible or number of operations you can do by applying only the simple axis of rotation. For example, let us take the case of BF3. Okay, so this is the BF3 structure of BF3, and you know, if you apply a C3 rotation axis in this molecule, you will have 3 arrangement, right? So 3 arrangement you will get. Then you already know that it has another perpendicular C2 axis for operation of that one perpendicular C2 axis, it will give one particular representation. So for 3 perpendicular C2 axis, it will give 3 different representation. So all overall representation is 6. So for this molecule, the operation of only simple axis of rotation. You can notice that I am not considering about sigma plane or A's. Only the CN rotational axis operation will give 6 different arrangements. So that means the molecule has a symmetry number of 6, and it is represented by W, right? So for BF3, which has D3H point group, it has symmetry number of 6. Whereas if you take ammonia molecule, so for ammonia molecule you can see in this case if you have only the C3 axis, right? So an operation of this C3 axis will give you 3 particular different arrangements, and it doesn't have any C2 axis. So that means no other arrangement is possible by operation of simple axis of rotation. So that means this molecule will have symmetry number of 3. So there is so for this molecule the point group is C3b. So there is a relationship between the point group and the symmetry number. You can see if a molecule belongs to C point group, so this H, V or D, that doesn't matter. You have to find out whether it is C or D. Okay, so if it belongs to C point group, then the point symmetry number will be same with the number of N. That is, for a Cn point group, the symmetry number is N. But if a molecule belongs to Dn point group, then the symmetry number will be 2n. Why? Because for Cn or Dn, every molecule has n number of different orientation due to the operation of principal axis of rotation. But in addition to that, for Dn point group, it will have additional n number of C2 axis, and that will give another n number of orientation, and for that this 2 factor comes. So this is very important. Now what is the importance of this symmetry of number, right? So if you remember the third law of thermodynamics, there is a relationship that delta S equal to K ln W. This W is actually the thermodynamic probability which comes from statistical mechanics, but we can replace this, we can represent our symmetry operation by the same W. That is, your delta S is proportional to symmetry number, right? So that means if your symmetry number increases, entropy change of the system increases. So the if a molecule has more symmetry, or that means it will have more symmetry number, and that in turn give higher entropy of the molecule. And you know, everything tries to maximize its entropy. So that means the system will be stabilized. Now how you can show that? So it can be shown by a very beautiful example, that you all know that these molecules like SbA5 or your let's say BF3, right? So these molecules are used in the superacid solution, right? So if you mix HF with them, you will have SbF6 and BF4 minus these anions, which are very stable. That's why these solutions are very much acidic. So the acidity of these solutions are results from these highly stabilized anions. Now, why these anions are so stable? So one thing is its thermodynamic stability, but another thing is stability due to increase in entropy. Because if you consider the SbA5, which has a TBP structure, right? So it has a TBP point group. TBP itself is a point group, but not TBP is a point group, but TBP belongs to D5H point group, right? So TBP is a D5H point group. So for this particular point group, the symmetry number is 10. Whereas when it goes to octahedral form, its point group increases from 10. Its symmetry number increases from 10. And the same thing is applied for BF3. When it is in the BF3 form, it has only it has D3H point group, right? So it has 6 symmetry number, but when it goes to tetrahedral form, its symmetry number increases. So whenever this situation occurs, that is going to a particular configuration, if the symmetry number increases, the system will always prefer to go that side. So this is one of the driving force for the stability of this particular anions, and this thing you will not get in normal books. Okay, so it is a very interesting factor. And if you consider any other species, okay, so let's say for example you know, for Xe, X6, X may be chlorine or fluorine, anything. So if you apply the valence bond theory to find out its structure, so you will find that it can have two structures. Basically its structure is octahedral. So Xc, it has an octahedral structure like this. Basic structure is octahedral, and now it has an extra lone pair. Now that extra lone pair may come through the face of the molecule or from any side of the molecule, and if it goes from the side of the molecule, then it will give a pentagonal bipyramidal structure, and if it goes from the face of the octahedron, then it will give a distorted octahedron. Now for these two particular structure, there is an equilibrium between these two, and which will be favored, that is dependent on the symmetry number of these two structure. That is, if the let's say the symmetry number of the distorted octahedron is higher than the symmetry number of your pentagonal bipyramidal structure, then the distorted octahedron will show majority in the equilibrium. Okay, so this is a very good concept. Symmetry number has a very good concept, so you should know that. Now today I'll finish my video here, and in the next video I'll be talking about the chirality, how chirality comes in a molecule, and the different projection formulas, mainly Fisher projection, Newman projection, and other things. So if you like this video, then give a thumbs up and share this video with your friends. And if you are new in this channel, then don't forget to subscribe my channel and also press the bell icon for getting the notification. So thank you for watching.